So, in our course selected topics in decision modeling, we are in our 29th lecture, that is quadratic programming. So, in this particular lecture, we are going to see the how this specific type of problem, that is quadratic programming problems, can actually be solved by a combination of the Karush-Kuhn-Tucker conditions and the linear programming principles, right. So, quadratic programming essentially what is this? A kind of problem which is looking very much like a linear programming problem, but with a difference. What is the difference? The difference is the objective function is quadratic in nature. The quadratic in nature means that it contains x1 square, xi square, xj square and xi xj terms where I is not equal to j, right. So, the quadratic programming problems essentially therefore, in vector form takes this, that maximize f x equal to c x minus half x to the power t q x, is it all right. So, where c is a row vector and x and b are column vectors. So, if c is a column vector also, then we have to write c transpose x as well, is all right. So, q and a are the matrices, right. So, essentially this is how the matrix form of the equations, but it will be very clear by taking an example what exactly this form means. So, supposing I have a problem, a quadratic problem, that is maximize f x equal to 15 x 1 plus 30 x 2 minus 2 x 1 square plus 4 x 1 x 2 minus 4 x 2 whole square, subject to x 1 plus 2 x 2 less than equal to 30, x 1 greater than equal to 0 and x 2 greater than equal to 0. So, this is a quadratic programming problem. Now, why it is a quadratic programming problem? Let us understand this. Now, from the nature of the problem, it is clear that C is 1530, because it was said that C is a row vector. So, C is in this way. So, C is 1530. X is a column vector. So, X is two variables x 1 and x 2, and supposing this is the form of Q and this is an A matrix and this is a B matrix, is it all right. Why A matrix is like this? Because it is a row vector, because there is only one constant. If we had more constant, then it would have looked more like a matrix, is all right, because there is only one constant. So, A is a simple form. Now, why Q should be like this? So, you see the objective function equal to C x minus half of x transpose q x, that is the objective function. So, this is how you evaluate. So, C is 1530, this is x 1 x 2 and half x 1 x 2. So, that is the transpose. See, this is a column vector. So, we transpose it, then write the q 4 minus 4 8 x 1 and x 2. So, basically it is a kind of matrix multiplication. So, what would be the matrix multiplication? It should be 4 x 1 minus 4 x 2 minus 4 x 1 plus 8 x 2. So, that would be this form, and this will be 1530 x 1 x 2. So, 15 x 1 plus 30 x 2. Now, this one, now what you can do? You see, let us do that. X 1 x 2 multiplied by 4 x 1 minus 4 x 2 minus 4 x 1 plus 8 x 2. So, if I multiply, then what do I get? First we multiply by x. So, 4 x 1 minus 4 x 1 x 2 that is what we get, and then by x 2. So, again minus 4 x 1 x 2 and plus 8 x 2 whole square. So, this is what we get 4 x 1 square minus 4 x 1 x 2 minus 4 x 1 x 2 plus 8 x 2 whole square. If I add these two, then we get 4 x 1 square minus 8 x 1 x 2 plus 8 x 2 whole square. So, this is what we get, but then there is a half. So, if I take half of this term, then we get 2 x 1 square, that is minus, because there is a whole minus. So, plus 4 x 1 x 2, that minus. So, this minus minus plus, and then minus of this plus. So, minus of 8 half. So, 4. So, this is the term, and then this is our C x term. So, you see that the original function, that is 15 x 1 plus 30 x 2 minus 2 x 1 square plus 4 x 1 x 2 minus 4 x 2, that would be, can be written in this form. Now, how to really get from here to here? See, these 15 and 30 is very clear. These 4 minus 4 minus 4 and 8, you can see that this is minus. So, there is a minus here. So, these 2, so that minus should be, these 2 should be double of that, and these 4 should be double of that, and these 4 should be divided 4 and 4 here in the minus form. All right. So, it is not really very difficult to really understand that how you can put such kind of things into these formats. Is it all right? So, essentially that is how we can really put the quadratic function problems into similar formats, right. So, we understood that why it is called a quadratic programming problem, right. So, in simple terms, we must understand that such problems are having an x 1 square terms, x 2 square terms and x 1 x 2 terms. So, and there is an inequality constant also. Such inequality constant in this problem there is 1, in another problem there could be more than 1. So, what exactly we do? So, if we have to solve them, first you see this is a maximization problem. These all the constraints are less than equal to 0 and the unknowns are greater than equal to 0. So, this is in the standard form. So, this standard form is very important, that point has to be remembered, that we must have the equation in standard form so that we can apply the what is known as the KKT conditions. Is it all right? So, you remember that to solve NLP problems with inequality constraints, we have to first put the problem in the standard form. So, if it is a problem of minimization, we have to make it a maximization problem. How? Minimize f x is actually maximize minus f x. Supposing these conditions are not less than equal to 30, suppose greater than equal to 30, then you can multiply both sides by minus and you can make it less than equal to 30. Suppose the variable is not greater than equal to 0, the variable is like in a slightly different form, again we can change them by suitably modifying the variables. Let us say by suppose x 1 is less than equal to 0, then you can take another variable say y 1 which is equal to minus x 1. So, if x 1 is less than equal to 0, then y 1 will be greater than equal to 0 and then replace x 1 by y 1 everywhere. So, we have to do some transformation to really put the problem in the standard form. Luckily, fortunately, this particular problem is in the standard form. So, if we have to take KKT conditions, then what we have to do? We have to really write the Lagrangian function first. The Lagrangian function for this would be L x 1, x 2 and u 1. So, we could have written lambda 1 also, no issue. So, it will be 15 x 1 plus 30 x 2 minus 2 x 1 whole square plus 4 x 1 x 2 minus 4 x 2 whole square plus minus u 1 into x 1 plus 2 x 2 minus 30. So, this will be our function. So, what we have to do? We have to then obtain del L del x 1 equal to 0, del L del x 2 equal to, at least we have to obtain this del L del x not equal to 0 really. We have to obtain del L del x 2 and del L del u 1. So, we have to obtain them because they will be 0 if we have equality constant. In this case they are not equality constant. So, we cannot equate to 0. So, let us take the differentiation first with respect to x 1. So, what we get? 15, then nothing here, minus 4 x 1 plus 4 x 2. So, this term is over and here minus u 1. So, can you see that this will be our del L del x 1. Similarly, let us take del L del x 2. So, if we take with respect to x 2, then we get 30 x 2. So, we get 30, then nothing here, plus 4 x 1 x 2, we take differentiation. So, we get 4 x 1. So, this is here, and then here this will be 8 x 2 minus 8 x 2, and here minus 2 u 1. So, you see this would be our del L del x 2, right. Lastly, we have to take del L del u 1. So, what will be del L del u 1? So, this term nothing. So, it will be x 1 plus 2 x 2 minus 30, actually minus of that. So, since the original condition basically we shall get, right. So, that is x 1 plus 2 x 2 minus 30 less than equal to 0, that is the 3 terms, right. So, basically the KKT condition says that these terms, these differentiation should be less than equal to 0. Additionally, x 1 multiplied by this, the differentiation equal to 0, x 2 multiplied by this equal to 0, and u 1 multiplied by this del L del u 1 will be equal to 0, right. So, that is essentially what we do. So, let us repeat exactly what we did. What we did is that first we formulate L equal to 15 x 1 plus 30 x 2 minus 2 x 1 square plus 4 x 1 x 2 minus 4 x 2 whole square plus u 1 times x 1 plus 2 x 2 minus 30. Then I get del L del x 1 equal to less than equal to 0, del L del x 2 less than equal to 0, del L del lambda del u 1 less than equal to 0. So, these are our these constraints, right, and additional constraint is x into x 1 into del L del x 1 equal to 0, x 2 into del L del x 2 equal to 0, and u 1 into del L del u 1 equal to 0. So, those are these constraints. So, these are the 6 constraints that we have already seen, and other than that all these terms x 1 should be greater than equal to 0, x 2 should be greater than equal to 0, and u 1 should be greater than equal to 0. So, these are our KKT conditions, right. So, this gives you a quick method of how to really find the KKT conditions for all such problems. Basically, you combine the equivalent of the Lagrangian function, make it partial differentiation, and those partial differentiation should be less than equal to 0, and additionally the corresponding variable into that differentiation should be 0. right. So, these are the 6 conditions apart from the non-negativity criteria. So, we get the KKT conditions. Now, once we get the KKT conditions, now see very interesting thing happens. Now, out of these conditions, let us forget about those equality constants for the time being, right, those dual constants, let us forget for the time being. Let us only look at the less than equal to constants, and let us give only attention to those problems only. So, what we get? We really get then 15 minus 4x1 plus 4x2 minus u1 less than equal to 0. Then the second one 30 plus 4x1 minus 8x2 minus 2u1 equal to 0, x1 plus 2x2 minus 30 less than equal to 0, and x1 x2 u1 greater than equal to 0. So, if you really look at the constants 2 and 4, something interesting you get, that if xj is not equal to 0, then the constant turns to equality. Suppose if x1 equal to not 0, then obviously this must be 0, that means the constant turns to equality. Is it all right? So, similarly, if u1 equal to 0, then the fourth condition satisfied, but if u1 not equal to 0, then this constant 3 turns to equality. Once again, if u1 not equal to 0, 3 turns to equality. If x1 not equal to 0, 1, this first one turns to equality. If x2 not equal to 0, then this one turns to equality. Is all right? So, this is the short form. So, basically then we shall work out with only these 5 conditions. Is it all right? So, let us see exactly what are these 5 conditions and what is their significance. So, we find that the significance will really be like this, that is, in this case we have these KKT conditions, these are our most 5 conditions. So, remember that from constant 2 and 4, this is the same thing that we have again written. If xj not equal to 0, constant 1 turns to equality. For j equal to 1 and 2, that means both this one condition turns to equality, right, and constant 3 turns to equality if u1 not equal to 0. Is it all right? So, these are some of the things that we actually have in this particular situation. So, what we can do? We can now add some slack variables, that is y1, y2 and v1, to make those 3 constants to equality. Is it all right? So, let us see exactly how they look like. So, you see we have this constant. So, if we add some slack, then we have 15 minus 4x1 plus 4x2 minus u1 plus y1 equal to 0, 30 plus 4x1 minus 8x2 minus 2u1 plus y2 equal to 0, x1 plus 2x2 minus 30 plus v1 equal to 0. So, what have we done here? We have added some, because they are less than equal to 0. So, if we add some quantity, that quantity could be our slack variables. So, in this case we have had 3 slack variables, that is y1, y2 and v1. So, if you add those slack variables, then we shall have this equal to 0. But something very interesting, that look here, that this constant turns to equality if x1 not equal to 0. Again from here turns to equality if y1 equal to 0. So, look at carefully. See, if y1 equal to 0, this is turns to equality, and if x1 not equal to 0, then it turns to equality. Is it all right? So, if x1 not equal to 0, then y1 equal to 0. Can you see this? Because in both the cases, if y1 equal to 0, this turns to equality. If x1 not equal to 0, then it turns to equality. So, therefore, if x1 not equal to 0, then y1 should be 0. Is it all right? But if you look at the other way around, if y1 not equal to 0, if y1 not equal to 0, then this equation has not turned to equality. That means, this is valid. Then what will happen about x1? Because you see, we had a constant, where this part multiplied by x1 equal to 0. So, if this is not 0, then x1 must be 0. So, that means, if y1 not equal to 0, then x1 must be 0. Is it all right? So, this gives an interesting thing that this fact and this fact, when you combine, then we get x1 star y1 should be equal to 0. Is it all right? So, once again let us repeat exactly what we said, that look here, this 15 minus 4x1 plus 4x2 minus u1 is less than equal to 0. Is it all right? If I add a slack variable y1, then this term becomes 0. Now, this will turn to equality if y1 equal to 0, and this will turn to equality if x1 not equal to 0, that we already seen. So, that means, if x1 not equal to 0, then y1 equal to 0. But if y1 not equal to 0, then this does not turn to equality, but then x1 multiplied by this portion is 0, that was constant number 2. So, from these two facts, if we combine, that is x1 not equal to 0, then y1 equal to 0, and if y1 not equal to 0, then x1 equal to 0, we get x1 star y1 equal to 0. And similar logic can be given between x2 and y2 for the second equation, and u1 and v1 for the third equation. So, that is x1 star y1 equal to x2 star y2 equal to u1 star v1 equal to 0. Is it all right? So, this is exactly what we get, and let us see how it combines. So, the KKT conditions for quadratic programming by adding slack variables y1, y2 and v1, the equations then become, what we did is, we have taken this 15 on the other side, and then minus 4x1 plus 4x2 minus u1 plus y1, that y1 is a slack variable, equal to minus 15, and 4x1 minus 8x2 minus 2u1 plus y2 equal to minus 30, and x1 plus 2x2 plus nu 1 equal to 30. So, now from the conditions 2, we can write x1 equal to 0 or y1 equal to 0, already we have seen the logic. So, x1 star y1 equal to 0. Similarly, for condition 2, either x2 equal to 0 or y2 equal to 0. So, x2 star y2 equal to 0, and for condition 4, either u1 equal to 0 or v1 equal to 0. So, u1 star v1 equal to 0. We can very interestingly combine them all, and we can get what is known as a complementary constraint in this way, that is x1 star y1 plus x2 star y2 plus u1 star v1 equal to 0. So, this can be called as complementary constraint, right. why it is happening? Look here that either x1 equal to 0 or y1 equal to 0, either x2 equal to 0 or y2 equal to 0, either u1 equal to 0 or v1 equal to 0. So, either of them will be 0. So, that means, if that whole total of this has to be 0, right. So, that these particular constraint would then ensure that this would actually happen. So, x1 and y1, x2 and y2 and u1 and v1 are called complementary variables. Is it all right? So, precisely that is how we can really create a simplex table out of this situation. Let us see how. So, we can again slightly reformulate this, that these are your original equations. So, but just remember that these first two we had negative value. We know for simplex algorithm we must have positive values everywhere. So, we can again make minus equal to plus, and then we can rewrite them as 4x1 minus 4x2 plus u1 minus y1 equal to 15, 4x1 minus 4x1 plus 8x2 plus 2u1 minus y2 equal to 30, and rest of the constants as they are, apart and adding the complementary condition. So, this is how we can actually get a set of linear constraints that we have to solve, right. Now, really how to solve them is, we let us take two artificial variables z1 and z2 really to get what is known as the canonical form. So, this is how an LP can be constructed, that is minimize z equal to z1 plus z2 subject to 4x1 minus 4x2 plus u1 minus y1 plus z1 equal to 15, and this plus z2 equal to 30, and this will be for 30, and all these variables along with this complementary condition. So, this is nothing but a linear programming problem and can be solved as an usual minimization problem. So, moment you can throw out the artificial variables from the basis, the solution can be obtained, right. So, solution of this is really not in our interest, because we know how to solve linear programming problems. The essential idea is that how the quadratic problems with the help of KKT conditions can actually be translated into a set of linear programming problems, because linear programming problems are easy to solve. So, quadratic programming problems can actually be having a modified simplex formulation, and that can be easily solved, right. This particular problem is solved in the Hillier and Lieberman book. So, what is really happening? We now have linear constraints along with those complementary variables. So, the idea is both cannot be coming to basic variables. So, we have a restricted entry rule. During the selection of basic entering variable, a variable will not be chosen if its complementary variable is already a basic variable. Choice should be made from other non-basic variables. So, we have from Hillier Lieberman book, this is how we have the modified simplex method formulation, and usual simplex rules can be used. We are not going deep into it, but if you form really follow the basic simplex procedure. So, this is table 0, then table 1, then we have table 2, and at the third table the solution is found, the artificial variables are thrown out, and we have x1 equal to 12 and x2 equal to 9 as the optimal solution, right. So, we stop here, and in our next lecture we shall see some real examples of Lagrangian multipliers and KKT conditions, right. So, thank you very much.